Creating randomization distributions. The p-value is calculated by randomization distributions. It simulates samples, assuming your null hypothesis is true. It calculates your statistic for each sample and then plots that. And then we find our p-value being the proportion that is as extreme or more in extreme than our statistic that we observed. So suppose we take a look at cocaine addiction. We had 48 people randomly assigned to either take a new drug or an existing drug. And then we observed how many people relapsed. So is the new drug or the existing drug really better for treating cocaine addiction? So go ahead and pause the video, write out your alternative and null hypotheses, and then write out your two possible conclusions. So we'll use P sub D and P sub L. Remember, your null hypothesis is that they're always equal. Now, we're trying to show that P sub D is less than P sub L, because if it's more effective, we're going to have fewer or smaller number of people relapsing, so that's why it's less than. So what are the conclusions? Well, we can either reject your null hypothesis that they're equal, and therefore the new drug is better than the old drug. Or we can conclude that we do not reject your null hypothesis, and basically we can't determine whichever one's better here, as in the new drug is not necessarily better than the old drug. So let's start out with our 48 people. We randomly assign them to the new drug on the left or the existing drug on the right. And we do that, and we get our two groups of 24. We conduct our experiment. We observe those that relapsed and collect our results. And then we have our results here. With the new drug, we had 10 people relapse and 14 no relapses. With the old drug, we had 18 relapses and 6 no relapses. So if we look at our proportions, 10 out of 24 for relapse and 18 out of 24 for our relapse, we subtract our two proportions and we get this. If the two drugs were equal, we would be expecting our proportion when we subtract it to be 0. Now the question is, if our null hypothesis is true and that it really is no difference, what are the chances of getting a difference in our proportions being this extreme? That's where you'd want to do your randomization distribution. And then look at your data value that you got from your sample to see how extreme it is. Now, your randomization distribution is always centered around your parameter of interest, either your proportion or your mean. So suppose we had this for your null hypothesis. Now, the question is it centered around our sample statistic or is it centered around our population statistic? Well, it's always centered around your population parameter, your parameter, which always refers to your population, so it's going to be centered around 12. So your randomization distribution is consistent with your null hypothesis, but we use the data observed from our sample. And that data that we use is really reflected in how we collected the data. If we had a bad collection result, a bad experiment, or bad randomization in our experiment, or bad way in collecting it from our observational study, our data is going to be bad and skewed. And that was talked about in our bias that we did in the beginning of the course. So we use randomness in our experiments by randomly deciding who goes into the treatment group and who's into the control group or the comparison group. If the null hypothesis is true, the responses should be the same regardless of which group they're in. And then we go ahead and simulate this by a random distribution. Resampling from our original data, getting our results, plotting it, and resampling, and so on. With observational studies, we do randomness by randomly sampling the population. And then we simulate by resampling the population, assuming our null hypothesis is true. So how do we simulate resampling for a population when we only have sample data? That's that bootstrap sampling that we did before. How do we do it to generate random samples for observational studies? We make our null hypothesis true, and then we do our bootstrap. So with Paul the octopus, that was a single proportion, and our sample size was 8. So it's like simulating it, flipping a coin 8 times and comparing your results of that. Cocaine addiction, that was an experiment. And we randomized by putting people into different groups. And we were keeping our responses fixed. As long as the original data is used and the null hypothesis is true for the randomization samples, then the method we get is, for the most part, going to be very similar for our p-values. It might vary slightly for each time we run stat key, but it's going to be very similar results. So we generate a random sample which is consistent with our null hypothesis using the data that we have, which also does reflect the way it was collected. The specific method will vary a little bit, but the general idea is always the same.